Good morning, everyone. Some people are still rolling in, but we're going to get started here. So welcome to Steam Management Showcase webinar series. We're excited for our presentation today on maximizing operational efficiency through strategic boiler selection, presented by our guest speaker, Adam Kellar. This presentation will focus on selecting the optimal boiler for your steam system, exploring different boiler types and their efficiency, and the impact on system performance indicators, including cost, emissions, and response times. This is a crucial topic for energy stakeholders striving to enhance steam system energy performance and reduce operational costs. We are Steam Management. We specialize in developing and implementing turnkey retrofit projects focused on optimizing steam systems and other utility systems for efficiency improvement. Our solutions are designed to significantly reduce energy costs, conserve water, and decrease carbon footprint for our clients through a holistic and thoughtful approach to each system's optimization strategy. We serve various markets nationwide, and we're committed to delivering tailored solutions that meet your operational and sustainability goals. Second. Hold on one second. I am Steam Management's Director of Engineering and Business Development and your host today, Chase Bean. Throughout the webinar, we will encourage you to actively participate, ask questions, and share your insights in the chat section. We'll have a few polls that will pop up today on your screen. Please participate in those. We do offer PDH certificates for anyone looking to verify their ongoing training. And the process for that is just to email me there at cbean@steammgt.com, and I'll send you that certificate after the presentation. As always, you can view this webinar once it's uploaded and past webinars on our website there at steammanagement.com/webinars. And we will have invitations for our next webinar coming out shortly, so keep an eye out for those. Founded in 1927, Miura has become the largest industrial boiler manufacturer in the world with a strong commitment to safety, efficiency, and reliability. Their approach offers complete steam solutions and lifecycle partnerships, ensuring that every stage from initial installation to ongoing maintenance is optimized for peak performance. By integrating advanced boiler technology with comprehensive support services, they help you achieve the highest standards of operation while upholding the values that matter most. Before we begin, I'd like to extend our gratitude to Miura for collaborating with us on the presentation. And we are excited to welcome Adam Kellar as our presenter today. Adam leads the engineering division at Miura America. He has 10 years of experience in steam and power generation, including working at a coal-fired power plant, as well as at an EPC firm executing major installation projects. As engineering division manager, Adam oversees contributions to boiler design, sales, and fabrication. He holds a bachelor's degree in mechanical engineering from Auburn University, War Eagle, by the way, and is a licensed professional engineer. His expertise in steam generation, combined with his practical experience in various industrial settings, enables him to provide insightful and effective engineering solutions. So thank you, Adam, for being with us here today. We are honored to have you, and the floor is yours.
Awesome. Thank you very much, Chase. Yeah, glad to be here. And War Eagle. Today we're going to talk about maximizing operational efficiency through strategic boiler selection. So what that means is basically we're going to look at the entire big picture and see what it takes to decide what the right boiler is for your application. So our objectives today, we're going to look through basically what are the common types of boilers. Hold on one second. Got something. All right. So what are the common types of boilers? What does efficiency really mean? So when we look at when we say the term efficiency, what are we really saying? And what are the typical boiler heat losses that go into that? What are we using to calculate that boiler efficiency? What are some hidden system efficiency losses that are missing from the equation? So what are we not taking into account when we just say boiler efficiency? Aside from fuel savings, what are some additional benefits of an efficient system? And how can I use all this to make informed boiler selections? So starting off with some common boiler types. There's most of these will be familiar to you guys, but the first type is a fire tube boiler. So basically, like it says, the fire and the flue gases are in the tubes. You've got flame within a large furnace here, and then the tubes pass through the volume of water. You've got water surrounding all those tubes, and the heat is transferred directly to the water that way. Contrast that with a traditional water tube boiler. You have the fire in the furnace, and the water is in tubes passing through it. Typically, your steam separation is occurring in a steam drum that usually has some heat applied to it as well. And then if there's a superheater, that steam passes into the superheater section, typically in the front part of the boiler here. But then the third type that doesn't really get mentioned often because it kind of falls under water tube is once-through water tube boilers. So this is either coil type. There's a few coil type manufacturers in the U.S. Miura is a once-through water tube boiler manufacturer as well. We have it's not a coil type. It's more similar to a traditional water tube, but it's still a once-through design. And what's happening is the water is actually boiling within the tubes itself. So that's why it's considered once through. There's not a internal recirculation within that boiler. So my expertise the last 3.5 years has been with once through water tube boilers. So I'm gonna try not to be too biased and talk about those too much, but that's the type that Miura generally makes.
So when you're saying, Adam, when you're saying once through, you're talking about the water is traveling through one time. Do you have multiple passes on the flue gas, or is that once through as well?
The flue gas is essentially once through. It depends. We have two different models, but essentially once through on one, and maybe you could consider it two passes on the other.
Okay.
And the water passes through the boiler once, and then there's usually secondary steam separation that occurs outside of the boiler. And in a Miura's case, that water recirculates back into the boiler. So it does pass through a couple of times potentially, but that circulation is not occurring within the boiler itself.
Okay.
And then in addition to those, you've got indirect boiler. Usually that's a hot water boiler. And so you're able to create essentially a closed loop for your water system where your boiling is occurring in this, or your primary heat transfer is occurring within the boiler. Hot water is exiting that boiler and transferring to a secondary heat exchanger here. And that is a very efficient design, but it really only is applied to hot water systems. And then you've got two different types of electric boilers. One is an electrode type where basically current is passing through the water and the resistance of the water is what's heating it up. And then electric resistance heating elements of the water is not being used as the heating element here. There's a sort of a resistive heating element within that boiler water volume. So I'm less familiar with electric boilers, but we will mention them here. For the rest of this presentation, though, we're mostly going to focus on steam boilers. So really these three types up here. The concepts generally apply to all types of boilers, but the kind of for the sake of examples and everything, we'll stick to fossil fuel fired steam generators. So.
And everybody, you should have received a poll pop up on your screen. You can participate in that. It's which type of boiler you're most familiar with. And these boilers are listed here. So
Great.
If you don't see it on your screen or you close it out, you can look at it again in the chat section.
Give everybody just a second to complete that poll. All right, so next we'll move on to efficiency. So basically, what is efficiency? So we've got some basic definitions. The first being combustion efficiency. So you'll often hear people say boiler efficiency. They sometimes mean combustion efficiency. So what that is the ratio of heat that's not lost through the flue gas stack to the heat that's input to the boiler as fuel. So you're ignoring basically the effectiveness of transferring that heat directly to the water. And you're just looking at how much heat did I take out of this gas before it exited through the stack. It's usually pretty simple to calculate. So it's a good one for that, but it's not really telling you the whole picture. Then you've got fuel to steam efficiency, which is similar, except now we're looking at what's the ratio of the heat in the steam to the heat that's coming in as fuel. So you're going to ignore intermittent losses like blowdown, shutdown and startup, things like that. But you are looking at how much heat am I actually getting out of the boiler. This one is a term that's not really used industry-wide as much, but it's a term we use at Miura often, and we're going to talk about it a lot in this presentation, and that's in-service efficiency. So that's the ratio of heat in the steam leaving the boiler to heat input as fuel over time. So it's accounting for all of the losses within the boiler and the kind of that main boiler part of the system. And then system efficiency is the ratio of energy to the process as energy as steam to the energy coming into the system as fuel, air, and water. And so that's really what the user is going to care about is how much heat am I getting to my process to make whatever my product is. When we talk about boilers, we don't necessarily have a full view into the system. So generally, we're going to talk about the first three when we talk about boilers, but it's good to recognize that that's the whole process. And then another term that you'll hear often in the HVAC industry, especially, is AFUE, and that's annualized fuel utilization efficiency. So that's an efficiency rating for combustion heating appliances. It's quantifying the ratio of the furnace's annual heat input compared to the annual heat input as fuel. It would fall somewhere in this range, fuel to steam efficiency to boiler in-service efficiency. My understanding is that it ignores a lot of the shutdown losses, a lot of the kind of intermittent losses as well. It's just a rating that I believe the EPA came up with, but it's commonly used as a shorthand for efficiency. It's maybe meaningful when you're looking at what the efficiency of that boiler itself is when you're not looking at the whole system. But it usually is only applied to hot water boilers and to HVAC systems. I know Chase has mentioned it a couple times in some of these webinars, so it does come up. So just be aware of what that is. Otherwise, we're not really going to talk about that today. Last couple, higher heating value, HHV, that one's probably a well-known term to you guys. So that's the amount of heat released during the combustion of a fuel that includes latent heat of vaporization of the water. So that's kind of the whole picture of how much heat is contained in that fuel. The lower heating value is the same, but it's ignoring the latent heat of vaporization of water. So you get, if you put efficiencies in terms of LHV, you're going to show much higher efficiencies. I think Europe and many other parts of the world use LHV. In the US, we typically use HHV. So it's just good to be aware of what you're looking at there. But so kind of visualizing a couple of these. So what does boiler efficiency mean? So typically it's either fuel to steam or combustion efficiency when someone says boiler efficiency. It's usually ignoring life cycle losses, so startup, shutdown, and blowdown losses. Maybe you're including blowdown, maybe not, but usually, and maybe you're including radiation and convection, depending if it's combustion or fuel to steam. But you're really just looking at that boiler efficiency at a brief period of time. In-service efficiency is essentially the same, but we've added intermittent losses like shutdown. We've added blowdown loss, and so we're looking at the whole life cycle. And excuse my sort of not great representation of a boiler here. So. And then system efficiency is kind of the whole system, right? So what we're really caring about is this energy out as steam to the process. When we look at the system, there's a lot of ways to capture the heat that we've got kind of floating around the system. We can have blowdown separator heat exchangers. We can have a flash tank. The flash steam can go to the DA or it can go to the atmosphere, and DA is obviously more efficient. You could have condensing economizer, a secondary economizer on the flue gas, things like that. But none of that really impacts what the boiler is doing. So it matters for the user. It's really important. But when we're talking about selecting a boiler, we're going to really look at boiler efficiency and in-service efficiency. And I think there's another poll question here. So if you guys
good catch.
That one before we move on.
Yeah, this one is, how do you currently measure boiler efficiency in your facility? So how are you looking at your system performance there with your efficiencies? Thing to know.
All right, and Chase, let me know if there are any questions in the chat or anything. Otherwise, I'll assume there aren't.
Yeah, no, that's just the poll. Yep, no questions so far.
All right,
I think it's interesting when you're looking at like all these different efficiency terms, because even using the same term can mean different things, like system efficiency, and then it's like, how much of the system are you incorporating? Are you talking about insulation losses? Are you talking about flash steam losses out in your condensate tanks? Or are you talking about just the boiler room? So it's very it's interesting to navigate sometimes when you're trying to compare things, don't you think?
Yeah, absolutely. You have to be careful where you draw the box. Make sure you make it a useful box. So
yeah.
All right, so we'll move on to standard boiler heat losses. So when we're talking about boiler efficiency, what are kind of the typical losses? And so we'll use the ASME indirect loss method to talk about that. Basically, that comes essentially from ASME PTC4, which is a performance test code. It's a pretty long code telling boiler manufacturers and customers how to kind of hold boiler manufacturers accountable for what they say they're going to sell you, and how do we measure that efficiency to prove that that's what we sold you. It uses it doesn't require directly measuring the steam output, so that's what's kind of nice about it, is we measure the combustion analysis. We measure how much excess O2 there is, things like that, and the temperature of the flue gas leaving, and combine that with a lot of assumptions and maybe some other measured or calculable values. And that way we don't have to put in a steam flow meter, which can be a little bit unreliable at certain flows, but kind of expensive to put in. So that's one nice thing about the PTC4 method. But essentially what you're getting out of that test code is an equation. It's not written this cleanly in the code, but basically what you're looking at is an efficiency in terms of wet gas loss, dry gas loss, radiation and convection losses, and then your higher heating value of fuel. It's also got a lot of other losses in there that are optional, basically, to take into account. We'll talk about what a couple of those are. But kind of the big point to make is that PTC4 is going to calculate fuel to steam efficiency at a steady state. So if you just look at that, you're only getting that boiler efficiency, what we talked about. So what do those terms mean? So dry gas loss is just the heat remaining in the flue gas constituents. You're going to exclude H2O for that part. So we calculate it based on CO2, O2, nitrogen, CO, and SO2. What's the heat of combustion of those elements? And we use the sensible heat of the stack. So we measure stack temperature and we can calculate dry gas loss. Same for wet gas loss. We're measuring the temperature in the flue gas, and as long as it's not condensed, then we can just use that as just sensible heat. And so it's the heat remaining in that flue gas water as both sensible and latent heat. Some other standard losses, you've got radiation and convection loss. So that's the heat lost to the air through the boiler casing. One important note that'll come back when we talk about in-service efficiency is that this loss is constant in terms of BTUs per hour, from 1% to 100% firing rate. So no matter what, it's going to be expressed, when you're going to see it expressed as a percentage of the max fuel input. So maybe 1% or 0.5%. But if you're firing at, say, half rate, then that percentage is actually higher, because your loss is going to be constant in terms of BTUs per hour. It's because your boiler casing temperature is always basically the same. It's always losing essentially the same amount of heat to the boiler room. The next loss would be blowdown loss. So again, this is sensible heat lost when the blowdown is drained from the boiler. So you've spent time, you've used fuel to heat that feed water that came in up to saturated temp. It's about to boil, and instead you're draining it. So you're losing all the heat that you've put into there. There are ways to capture it, like we talked about, but that's looking at system efficiency, not boiler efficiency. And blowdown loss is system dependent. So we're usually going to exclude that from a stated boiler efficiency, because a boiler with a 10% blowdown is going to have a significantly different efficiency if you account for blowdown loss than one with 1% blowdown. And that's not going to be dependent on the boiler design. That's really dependent on water quality and things like that. Some other losses that PTC4 talks about especially are unburned carbon or LOI, loss on ignition, formation of NOx. There's a few others that are relatively small when you look at the whole amount of losses in the boiler. So for an example, let's find the fuel to steam efficiency of a boiler. We're going to say it's operating at 100% load on natural gas with 300-degree flue gas temperature, 5% excess O2. So we're going to say higher heating value of that fuel is 1,000 BTUs per SCF. Ambient temperature is 80 degrees, and we've got a radiation loss of 0.5%. So we're going to ignore all the other losses for this. We're just going to say what is dry gas, wet gas, and radiation loss, basically. So dry gas is flue gas enthalpy times the difference in temperature of that flue gas to ambient, and then multiplied by the dry flue gas volume per unit fuel. So it's all going to be expressed in terms of per unit fuel. And what you come out with when you calculate the constituents in the gas, you measure the temperature of the flue gas, which we were given, and then you use some kind of constants for combustion of natural gas, you get 49 BTUs per SCF. So that's your dry gas loss. Your wet gas loss is similar. You're looking at the water, the amount of water pounds per SCF of fuel, which is a standard constant value that we know from experimentation and everything. And then the enthalpy of the vapor at 1 psi in flue gas temperature minus the enthalpy of vapor of the liquid at ambient. So this is telling you what's the latent and sensible loss of that evaporated water. So anytime you have combusted in a fuel air mixture, you've created steam as part of that combustion process. So we get 107 BTUs per SCF. We plug all that back in. We divide by the HHV. We subtract out radiation loss, and we're going to get 83.8% efficient. So this is a pretty efficient boiler. That's generally going to be a good efficiency. You've got a well-designed heat exchanger. We're probably going to be pretty pleased with that. So what are some ways to improve boiler efficiency? So that's kind of the whole picture of boiler efficiency. So how can we make it better, especially on an existing system? So some cases you can add an economizer to capture more heat from the exhaust, or maybe a secondary economizer, depending where you're putting that heat. You can maintain proper water quality. That's going to prevent scale buildup. Scale can reduce the effectiveness of your heat exchanger. So that's very important. That's going to, over time, gradually decrease the efficiency of your boiler. You could upgrade the upstream water treatment equipment to reduce blowdown rate. So if you go from a water softener system that's maybe a little undersized or something, you might be blowing down 10%. Expressed as a ratio of incoming feed water. If you change that to, say, a reverse osmosis system, an RO system, you might reduce that blowdown rate down to 1%. So that's going to be a pretty significant savings on fuel input. You can upgrade the boiler casing and the insulation on the boiler. So if it's an older boiler, it might not have very high quality insulation, so you might be losing a lot of radiation loss. If you do something like that, you definitely want to at least discuss with the boiler manufacturer or an engineer, because you can impact the sort of firing characteristics and heat exchange characteristics of that boiler, but it's definitely an option on older boilers. Or you can tune the burner controls. So depending what your emissions limits are, you may be able to reduce excess air a little bit and stay within your emissions limits. And less excess air is going to generally give you higher efficiency. So I think we have a poll again here before we move on to other system efficiency losses.
Yeah, have you considered or implemented any of these efficiency improvements in your facility? So adding an economizer, upgrading water treatment equipment, enhancing boiler casting or insulation, tuning burner controls. None of those yet, but planning to. Also, by the way, just back to the other polls, the people who were most familiar with the fire tube boiler by a good bit. That was 57%. And the next highest was the once through water tube and indirect hot water. Well, that one, once through water tube, traditional water tube, were all 14%. And then as far as the system efficiency question, people say they're using system efficiency the most. Well, that's interesting.
Yeah, that's good.
This one looks like the most popular efficiency improvement is adding an economizer, 44%. Interesting.
Yeah, that's definitely going to have a pretty good impact. It's usually 3 to 5% increase in efficiency when you add an economizer. So that's good. Okay. So next we're going to talk about some hidden system efficiency losses. I call them hidden because they're not included in that boiler efficiency number that you usually see from a manufacturer or from a spec or something. So the first one is startup and shutdown losses. I lump them together because they kind of can cancel each other out at times. But anytime a boiler is shut down, the water and steel in that boiler remain hot. So if that boiler is not restarted within a few hours, it's going to gradually cool completely. You're going to lose that energy into the boiler room or through the stack, and so you're not going to ever get that back. And the magnitude of that energy released corresponds to the weight of the warm steel and the volume of the water contained within the boiler vessel during normal operation. Similarly, when a boiler's restarted after a shutdown, it's going to take time to warm up the boiler, to warm up that system. Depending what you're doing with that heat, you may be dumping steam, or you may be blowing down a lot, or returning condensate that then sits in a tank. So you may lose heat that way as well. But startup losses are a little more difficult to calculate, but they're a significant loss as well. Another big important loss is purge loss. So depending on the boiler size, fuel type, what jurisdiction you're in, you're probably going to require both a pre-purge and maybe a post-purge. Depends on the fuel type. And what that means is you're passing 4 air volume changes through that furnace. So you're blowing ambient air through a hot furnace, usually hot if it's a post-purge after you've shut down recently. And then you're basically making that boiler operate backwards. You're taking heat out of the water and out of the steel and putting it into the air that's going through the stack. And so it's difficult to estimate that magnitude without testing. You can test the temperature of the exiting gas during a purge cycle, things like that. You can sometimes, if you understand the boiler details a little bit, you can calculate it. But generally speaking, a smaller furnace is going to have less purge loss because you have less airflow required during a purge, because the code is usually stating 4 volume changes. Sometimes there's a minimum time limit, so maybe that advantage is negated a little bit. This is usually a pretty small percentage of total loss unless you have a very cyclic system. So maybe less than 1%, maybe even much smaller than 1%. But this, it can add up if you have a cyclical system that keeps shutting off and starting up a boiler. Another important one is hot standby loss. So this one is a system where standby capacity is required. You basically have 2 options. You can either oversize a single boiler and operate with available capacity. So you might operate at 50% load and be ready to ramp up the boiler quickly to catch up with whatever your demand is. Or you could install 2 boilers and keep the second one hot, ready to start up quickly. So that's going to sometimes will reduce your capital cost. It gives you some inherent N+1 redundancy, but you've got to keep that second boiler hot. And so you're going to constantly be adding a little bit of fuel, burning a little bit of fuel in that boiler. That boiler is always going to be losing heat to the atmosphere because of radiation loss. So you're going to be wasting fuel that way.
Hey, Adam, I got a couple questions.
Yep.
On the previous slide, can you explain to the listeners why the purges are required?
Yeah. The point of purge is for safety reasons, right? So at the end of combustion, you might get a little bit of unburned fuel sitting in the boiler. It might be in some pocket that doesn't get great airflow. And so if you don't purge, then if you just light off a boiler with stagnant air in it, you could ignite that excess fuel. You can get a puff that can do all sorts of damage to the furnace, or blow off the stack, things like that. So it's safety reasons to prevent explosions.
Yeah, and your burner flame safeguard is going to control those purge times, and that's not something you can adjust to improve efficiency. So it's it's a necessary loss that is unavoidable. Well, the only way to avoid it, I guess I would say, is to try to minimize your cycling, right? So
Yep. Minimize cycling, or select a boiler with a small furnace to begin with. But again, it's not going to have enough of an impact usually to make your decision for you in that case. But
yeah,
it's a good question. Right, so we talked about hot standby loss. So let's do another example.
Oh, I was gonna ask something on that. So in the picture there, you're kind of showing like just keeping a boiler on low fire.
Mhm.
Is that your typical approach, or do you do like warm up coils, or how do you guys usually approach that?
It Miura, we don't really do it because again, we're supplying the boiler, we're not designing the system. But it can be done a number of ways. Yeah, usually I'll see a boiler operating in really low fire just for a minute to warm it up, and then it has some set pressure that as that temperature drops, the pressure drops a little bit, and when it reaches some pressure, it'll come on again. But yeah, it can be done with warm up coils, which is running a little bit of steam through that boiler to heat it up. It can be keeping the boiler in a very, very low fire, if it's got a high turn down. So there's a few different ways to do it depending on the boiler type and the system needs.
Yeah, cool. Thanks.
All right, so an example. So we're going to look at in-service efficiency of 3 very similar boiler systems. So they're going to all have the same total capacity. We need 900 boiler horsepower, and we need that full capacity to be available within about 10 minutes. So if the first boiler shuts down, or if there's a large spike in load, we need to be able to catch up very quickly. It's going to be 450 boiler horsepower at normal operation, so kind of average load is going to be half the max. 100 psi saturated steam, so pretty straightforward system. We're not going to have a superheater or anything like that. And then a deaerator operating at 3% or 3 psi or so for 220 degree feed water. And we're gonna, for the sake of this argument, we're gonna say that all boilers are operating at 83.8% efficient at max load. So that's what we calculated in the first example. We're gonna say there's really no difference in the sizing of these boilers. They've been selected for the exact best efficiency at this load. All are the same. They're going to operate 12 hours a day, 6 days a week. So we're going to shut down once per night and then for a whole day on the weekend. We're going to say they're all operating at 5% blowdown, and they all have 0.5% radiation loss. So system 1, we're going to say let's do 1 900 boiler horsepower fire tube boiler. We've got the built-in capacity there. For system 2, we're going to say 2 450 boiler horsepower fire tube boilers. They're going to have the second boiler is going to remain hot to be ready to come up to full load. And then the third system is going to be 300 horsepower small water tube boilers.
Hey, Adam, I don't want you to stop and answer this question, but there's a question that is, what would be the most efficient load for a boiler? Which is I think that's what you're going to be getting at here in a second. So keep that in mind. Somebody has that question, but I'll let you finish the example that it might answer it for them.
All right, yeah, I think we'll sort of answer it, and then I'll go back to it. Don't let me forget after this slide.
Okay.
All right, so here's the results. We're not going to go into all the details of how they're calculated, but let's look at some kind of notable differences in each system. So the biggest one that's noticeable right from the start is the small water tube boiler. Is very small, right? It's got very little water contained within the boiler. Its weight is a good bit lower. So because of that, we've got lower shutdown losses, lower standby losses for this system. The 2 bigger systems have much higher inherent shutdown losses and standby losses. So if you have a system that has those losses, then that's important to keep in mind. Another important point is that the small water tube boiler can start up very quickly in under 5 minutes. So we don't need to be keeping it in hot standby. We're able to bring up that third boiler from cold very quickly. So hot standby losses are 0 for the small water tube system, whereas the System 1, the boiler is always hot, so there's no hot standby losses. Then system 2, that second boiler is going to be losing energy to the atmosphere at all times. And a really important note is that the highest average fuel to steam efficiency is actually on the least efficient system overall. So the system 2, which is two 450 boiler horsepower fire tube boilers, the fuel to steam efficiency is that 83.8% efficiency that we talked about, because that boiler is operating at its max load. It's where we sized it for, right? However, in-service efficiency is much lower because that second boiler is being kept hot, and you've got very high shutdown losses here as well. You also have a very high efficiency on both other systems. So if you're just looking at fuel to steam efficiency, you might think that that's your best boiler. System 2 might be your selection. But if you do that, then you've really selected the wrong boiler for this system. The other two are a little bit better. So important to always remember, the highest boiler efficiency does not equal the lowest fuel cost inherently. You have to look at the whole system efficiency. So to answer the question that just came up in the chat, the highest efficiency point is a boiler that never comes on at all, right? That boiler has not lost any fuel. But ignoring that, the next highest can be anywhere, right? It's usually, I think it tends to be in the low to middle fire range is where it actually kind of peaks. But every boiler operates a little bit differently. So you have to look at each boiler individually to see where its highest boiler efficiency point is. Some manufacturers can help you, determine that and figure out how to size your boiler so that it tries to run at the highest efficiency point all the time. But yeah, it can depend a lot on a number of factors in the boiler. So.
And it certainly varies between, steam boilers and water boilers, right? I mean, that's not the same. We're not talking about the same game at all when you switch between those two, right?
Yeah. And I have a lot less experience with hot water boilers, so I can't really speak for those too much. But yeah, my understanding is they can be also a lot more efficient because you can condense in the back pass and stuff like that. But
yeah. And then that condensing is what really drives the high efficiency of those boilers, and that can vary by external factors to the boiler, not just the load percentage. So it's, you're returning water, temperature, and things like that. But anyway, that's not what we're talking about here.
Yeah. No, it's a good point though. It's the hot water boiler efficiency, advertised efficiency, will be much higher typically than a steam boiler. And yeah, there's a number of reasons for that, but the main reason is the fact that you can have it condensing, and you're not going to, you're not getting bad water quality within the hot water boiler because you're not actually having boiling occur. So you're not having cycling up occurring the same way as you do in a steam boiler. So. All right, so ways to improve that in-service efficiency. So, if you've got a system already installed, what can you do? Well, we can look at your off-peak needs, right? So maybe you're keeping a boiler hot overnight. Is that really necessary? It might make more sense actually to bring somebody in and start it up early in the morning. Things like that. There may be ways to reduce how much boiler you're using during that off-peak time. Because that off-peak time is when you're really often wasting a lot of heat because you've got a very oversized boiler. Eliminate hot standby would be a great way to reduce or to improve in-service efficiency. That's not always possible, but maybe you can reduce that hot standby pressure or temperature. Maybe you don't really need it to be able to instantly ramp up. Maybe 5 minutes is okay, and you can reduce that pressure temperature a little bit. It's not going to cycle the burner quite as often, not going to use quite as much heat. So that's an option. Maybe you can look at your boiler operating trends, and maybe you're operating really below 50% capacity with multiple boilers. So maybe you can turn one of those boilers off actually and keep it off more for more time. Just depends on the system, right? So again, every system is different. You can't say inherently how to improve in-service efficiency without looking at the system, but Chase is really good at helping you out with that. So. All right, and the kind of last topic before we wrap up and get into kind of conclusions here is what are the added benefits of an efficient system? So obviously we know about fuel cost, and that's very important. But what else are we getting out of it? So emissions, right? So efficient systems inherently have lower overall emissions when you measure them over time. So you can tune a burner to reduce NOx, CO, and SOx. Carbon dioxide really can't be tuned out. It's basically constant based on million BTU per hour input. But if you have two boilers that have the same emissions ratings in pounds per million BTU an hour, pounds per million BTU, or in ppm, if one boiler is operating at 80% efficient and the other one's operating at 70% efficient in terms of in-service efficiency, the more efficient system is going to produce 10% lower emissions because you burnt 10% lower fuel. So kind of intuitive, but it's important to remember. It gets overlooked a lot when you're looking at just the spec on that boiler. They may both have 9 ppm NOx, but whichever one is more efficient is going to produce less pounds of NOx or tons of NOx over time. So higher million BTU per hour input means higher emissions. The next is time saving. So we talked about how quickly a small system can start up. And so a system that takes less time to heat up and cool down can reduce the number of hours that you've got to work, that an employee has to come in. So especially if you're shutting down overnight, you might be bringing somebody in an hour and a half or so early before you really start production, just to start the boiler up and make sure it ramps up. But if you have a system that can start up very quickly, you can save maybe $25,000. Just did a back of napkin math based on average boiler operator wages. They're in high demand right now. They're demanding really high hourly rates because it's hard to find people. So that can be a really big savings for an operation. And frankly, people don't like to work overtime that much anyway sometimes. So another one is load response. So an efficient system is just going to inherently adjust to changes in load more nimbly because there's less thermal inertia to overcome during load swings. A large boiler
Adam,
yeah.
I got another question in the chat here.
Yeah.
Can you compare the partial load efficiency using 3 small boilers to using 1 big boiler? How would you comment on that?
The partial load efficiency?
Well, I think they're saying using 3 small boilers to cover the load versus 1 big boiler, and turning that 1 big boiler down, and like you know what I mean. If you're at 60% of the capacity, using 2 small boilers at full load, or 1 boiler at 60% load, like what?
Yeah,
I guess he's just saying comment on that.
Yeah, it definitely depends on how much that load is changing. But if it were perfectly constant and that third boiler never comes on, and that large boiler is not ramping up and down, probably the large boiler turned down is going to be slightly more efficient if you never have shutdowns, because the boiler is usually a little bit more efficient at that lower load. So you might have a little bit better efficiency. It's going to depend a lot on the system, though. It's hard to say a blanket statement. That's a good question. I mean, a smaller boiler is not always the best solution. I don't know if any of my sales guys are on here. They probably don't like that, but it depends on the system. You have to take every system on its own and look at it and make the best decisions for that application.
Yeah, every system is so unique, and not just with boiler selection, but with all of your auxiliary equipment required. Just all the decisions that you have to make to try to improve your efficiency. It's always a case by case thing, and that's why guys like me and Adam really enjoy working on steam systems, because it's challenging. But yeah, I totally agree.
Yeah, it's a good question though. All right, so on load response, large boilers can overcome that kind of inherent inefficiency, if you will, because they have a large steam drum or a large volume of water that basically acts as an accumulator. So as pressure in a system drops because steam load's increasing, it's going to just boil off more water out of that boiler. So that's overcomable, but it's inherently got more thermal inertia within it. So a responsive boiler system is going to help maintain a stable production process. So if you can maintain that constant steam pressure if you're going to maintain constant steam temperature inherently. So that's going to help maintain a stable production process for whatever you're using the steam for in the facility. So, and last, maybe a little less directly related to efficiency, but still I think worth mentioning is safety. So a boiler with a small furnace and a low water content is just inherently safer because you've got less stored energy, and stored energy is a function of operating water volume, right? So you've got all this water very close to boiling that is just being stored within it. So less energy stored within a boiler is a safer boiler inherently. So that's something to remember. You know, less energy stored generally makes it more efficient. It also generally makes it safer. So looks like we have another poll here before we move on to kind of the last couple slides I've got.
Yeah, what would be the most significant benefit of improving your boiler system's efficiency? And again, this question is for the listeners. Lower emissions, time savings, better load response, increased safety, or cost savings? All those are important, so this is kind of subjective. What do you guys think there? Got a lot of better load response. Interesting. Or two. Yeah, 18%. Cost savings. There we go. That's what I was expecting.
Yeah, I was expecting cost savings. Yeah.
Yeah, cost savings. That's what everyone likes. Okay. Other ones are very important too. We should get a couple votes for safety there. That should definitely be priority. But yeah, cost savings. That's what we're doing, right? We're trying to improve efficiency to reduce costs. Okay.
All right. So kind of last thoughts, bringing it all together, hopefully. What are the considerations when selecting a boiler? So kind of our typical recommendations based on different needs. So if you're looking at operating schedule, so if you've got overnight shutdowns, you're probably going to want low water volume boilers because you're going to inherently have less shutdown losses. That's going to be a very significant impact to your fuel cost. But if you've got 24/7 operation, a large fire tube or a large water tube boiler might fit your needs a little bit better. You're not going to see that big 4, 5, 6% loss. So it's not going to, the math's not going to be as easy there. If you've got a large difference in your average load compared to your max or your min load, or if you've got some seasonality, that's gonna impact what we're gonna select. So if you've got low off-peak demand, you probably want a modular system where you can shut some boilers off. Maybe you lay up a boiler for the entirety of summer and you don't lose any heat that way. Versus if you've got steady load, a single right-sized boiler is often going to be the right choice, and you're going to size it so that it's going to operate as efficiently as possible and weigh that with your capital expenditure. So again, depends a lot on a lot of different factors, but you might look at ramp rate. So if you need to be keeping boiler capacity available for a quick load spike, you might look at a small water tube, or you might look at a small water tube with kind of modular boilers, so you've got some available. Or you might say that the load is so quick and recovers so quickly that a large boiler with a very large steam drum might make sense. So and then available space. So if you've got a high cost per square foot, if you've got small available footprint, a water tube is probably going to make sense, whether that's traditional or a small once through water tube. So there's kind of a lot of different factors to consider, and it helps to have somebody like Chase or us take a look at it and see what your needs are. But it's once we gather enough information, we can definitely make an informed decision. So. And so we'll bring it all back to that first slide, which was each type of boiler. So what are some generalized strengths and weaknesses? So a fire tube boiler, I think it was 58% of you guys said it's what you're most familiar with, and that's a big advantage, right? It's it's conventional design. A lot of mechanics are used to it, maintenance people are used to it, so there's some familiarity, and that's valuable. It's going to respond really well to load spikes because it's got a large volume, but it's also going to have large shutdown losses. It's tube replacement's very easy. If you have a problem with it, you can take out a tube or plug a tube depending on the design. And it's going to have a little bit slower startup than other designs. Whereas a traditional water tube is load response is going to depend a lot on drum size, its firing ability to absorb rapid firing rate changes. But you can be able to go a lot higher pressure range than these other types. It's almost always the best for very large applications, right? If you've got pretty much every fossil-fired power plant in the country that has these massive steam outputs, they're almost all water tube boilers, right? Because it does make sense at that very large application. Once through, water tubes have a really small footprint, so they've got a fast load response. They can be modular install. They can, you can expand capacity without expanding the size of the boiler room often. So they're good for that. Tube replacement can be really difficult, sometimes impossible. Sometimes you have to replace the whole pressure vessel if something goes wrong. So that's definitely a weakness. But you have extremely fast startup, so you are able to respond to changes in your demand very quickly. Indirect systems, they're hot water only. They're extremely efficient, though. Like I said, they can be the condensing type. Their efficiencies can be higher than 95%. Sometimes you see 98, 99%. Electrode and electric resistance. So electrode boilers are really high voltage, which is kind of a downside, but they're extremely efficient. But that doesn't mean a lot when you're paying, a bunch for electricity. So they have really high operating cost. In the US right now, they generally don't make sense when you're just looking at cost, just looking at operating costs. But, in the future, we'll definitely see more and more of those. And then electric resistance heating element, same thing, very high operating costs, extremely efficient. I think kind of they're generally a little bit lower output than an electric boiler, but they're also have their advantages in the electric market. So, yeah, that's all I've got. I hope I was a little bit informative and maybe taught you guys something, and maybe just filled up an hour for Chase. But anyway, if you have any questions, please let me know. Otherwise, we'll hang out until you guys are done. But thank you guys for your time.
That was fantastic. Good job, Adam. And I wanted to add to the modular boilers. I love the redundancy also. So when you talk about a big fire tube boiler, you blow a tube, then you're down, right? So if you have a bunch of smaller boilers covering the load and one of them goes down, you're generally still going to be able to cover your load unless you're just maxed out. So, but yeah, I just wanted to add that to the last slide. But yeah, thank you so much, Adam, for coming. We will hang on probably till about noon and answer any questions, and feel free to put those in the chat if you do have any additional questions. Again, the PDH certificate, you just email me right there, cbean@steammgt.com, and I will return that to you. And we appreciate all of you attending. This was a great installment in our series, I guess you would say. And we look forward to seeing you at the next one. And feel free to reach out anytime with any questions or any applications that you could use help with. And yeah, we'll hang out for a little bit. Adam, how do you so there's all these ways to improve efficiency. I think that one thing that clients have a hard time wrapping their head around is like measuring and monitoring their system performance over time. Do you guys have like recommendations in that space, or maybe even monitoring products, or is that something that you get into a lot, or are you just more about improving the product efficiency?
We're mostly focused on, well, at least my group is mostly focused on improving the efficiency of the product. But we do try to become a life cycle partner. So we do look at efficiency over time. Obviously, if you can measure fuel input, if you can measure water input, then you can basically calculate efficiency that way, and you can trend that over time. We have some IoT systems that we put on all of our equipment that we sell. We try to sell along with an IoT system. It's called our Miura Connect. And that's a big one for us to kind of monitor. We can see it on the maintenance side at Miura, as well as the customer can get alerts and pay attention to stuff over time. We're starting to introduce some features to that involve actually, a monthly checkup by maintenance, just to see, hey, what's going on here? What are the trends showing us? Is there anything we need to take a look at closer? So yeah, it's mostly monitoring, and keeping an eye on things is where we kind of start with. But there's all sorts of opportunities that I know you're familiar with, of kind of walking the plant and putting a temperature gun on steam traps and things like that, and seeing where you're maybe losing efficiency in your system. So
yeah, definitely. Yeah, that's interesting, the monitoring. So that's external to the boiler. You're monitoring different process parameters and kind of putting it all together to monitor efficiency. Is that what that product is doing?
yeah, basically it's taking signals from the boiler and compiling them, and then it's taking signals from our water treatment equipment and some of our other monitoring devices. It can take pressure, temperature, things like that. It can take some other inputs. You can put some of your other processes in there, depending what they are. And yeah, it's kind of putting them all in the cloud or in your BAS system.
Very cool.
Yeah.
Very cool. That sounds very useful. I think that a lot of steam system owners, they just lack insight into their system, and it's really neat to kind of see things brought up to speed. I think steam systems generally lag way behind other utility systems in that area, so it's pretty cool.
Yeah, it's we've had that product for maybe 3 years now, and it's been really good for us. I think we've had a lot of success being able to kind of help customers, keep an eye on their systems and see when things are going wrong. So yeah, it's been good.
Somebody asked that water purity is more critical for Miura boilers compared to others. Is that, and why is that?
I would say it's sort of not. So the water treatment requirements for all boilers are basically the same based on ABMA. And we use the same water treatment recommendations that every other boiler manufacturer does. The biggest difference is if you mess up on a fire tube boiler, you're basically just going to accumulate scale or whatever impurities on the outside of tubes, and so you're not going to obstruct flow. Whereas because the boiling in a Miura boiler is occurring within the tubes, any separation of steam that results in a deposit of scale or something like that is going to risk plugging that tube. And so once you plug a tube, you fail a boiler. And so that's why we do have that perception sometimes in the industry. And it's a little more sensitive to bad water quality. Its water quality requirements are actually the same as every other boiler. But you do really have to keep an eye on your water quality and make sure you're doing your regular maintenance and keeping up with it. But you should be doing that on a fire tube. Really, the stakes are higher in some ways because a failure of a fire tube boiler can be much worse. But the failure occurs much later. You see it in efficiency losses in a fire tube boiler versus in a Miura boiler, you might not see it until you get an alarm on the scale buildup, and then you got to clean the boiler. Or worse, you might have a failure, if you ignore some alarms and stuff. So
Yeah, so in a fire tube boiler, it'd be happening quietly for a long period of time, but you're living with those diminished efficiencies, and then
exactly.
eventually you might get a tube failure anyway.
Yeah, exactly. And then in a fire tube, you replace the tube, and then you go right back to where you were, right? And over time, that's going to add up to the cost of a pressure vessel, probably. But you're just going to do it in incremental change outs of tubes, which is just a different way to spend the money, right? So if you're not taking care of your water, it's going to be costing you either way. It's just whether or not it's going to be a capital expense that's going to hit you unexpectedly one year or not. So
Cool. All right, well, that's 12 o'clock. I'm not seeing any more questions. Thank you again, Adam, and thank you everybody for attending. We're going to close it out, but if you do come up with any questions after the fact, feel free to email me or email Miura there at those email addresses. And we thank you again for attending, and have a great day.
All right. Yeah. Thanks, everybody. Have a good one.